Good morning, sir.
Good morning, madam.
Good morning, sir. We welcome you all to the second section of Day 2 Faculty Development Program sponsored by AICTE Training and Learning Academy on Novel Materials for Next Generations. It's the time to introduce our chief guest for this section 2. I am extremely honored and privileged to introduce Dr. K.P. Ilangu sir, Professor, Department of Chemistry, Gandhigram Rural Institute, Gandhigram, Dindigul. He done his MSc and MPhil degree in chemistry from Annamalai University and doctoral degree in coordination complexes from Gandhigram University. Dr. K.P. Ilangu sir is a veteran in teaching with 30 years of experience. Sir has published 209 articles in reputed scientific journals. 20 doctoral scholars have graduated under his direct supervision. 7 scholars are currently doing PhD under his supervision. He completed 2 CSIR, 2 UGC and 1 Government of India major research projects. He received UGC Mid-Career Award and now he is the Director, University Instrumentation Center. His research interest areas are coordination complexes and optical sensors. I am happily inviting Dr. K.P. Ilangu sir for the technical section 2 entitled on coordination complexes as sensors. Now the section is open. Over to you, sir.
Thank you, madam, for your nice word of introduction.
Yes, sir.
Is screen is visible?
No, sir.
Please. I think now it's visible.
Yes, sir. Yes, sir.
So, good morning, friends. This is a continuation of my previous lecture, yesterday's lecture. Metal complexes. In the title, it is given as metal complexes as ion sensors. But here in the presentation, I have given as fluoride ion sensor. Since I am going to concentrate only on fluoride ions, I have modified the title little. Okay. So, I don't know whether you have enjoyed the session yesterday. This is the continuation of that ion sensing work. Okay. So, yesterday we have seen that anions plays a vital role in physiological functions as well as they are extensively used in industries. We have seen some anions are biologically significant one. We are very much in need of these anions. These anions are essential anions. They are non-pollutants. Even at higher concentration, they will not affect our biological system. They are non-pollutants, particularly these 3 anions. Then some of the anions which are commonly used in industries as well as in day-to-day activities are pollutants even at very low concentration. Yesterday we have seen some interesting facts about cyanide, which is a lethal poisonous anion. So even small amount of cyanide can cause death. Okay. So as I told you earlier yesterday, I have reserved one ion, the fluoride ion. So some anions are essential, some anions are toxic pollutants, and this anion is a special anion, fluoride ion, has dual role. Okay, so now today we are going to concentrate more on exclusively on fluoride ion. As we know that fluoride ion occupies the extreme right corner of the periodic table apart from the noble gases. So it is highly electronegative naturally as it occupies the corner of the periodic table. Don't underestimate fluoride ion since it is occupies, though it is occupies a corner in the periodic table, it has its own significance. Okay, so today we will be concentrating more on fluoride ion, and I will give some facts, some interesting facts about fluoride ion first, then we will move to the second part. We will move to the sensing of fluoride ion, detection and determination of fluoride ion. So as far as our inorganic practical is concerned, we have a round of tests, only a simple test for fluoride ion. We have calcium chloride test. What we are doing is we are adding calcium chloride into a solution of fluoride as well as oxalate. Fluoride gets precipitated as calcium fluoride and oxalate gets precipitated as calcium oxalate. After adding sulfuric acid, it releases fluoride ion, and calcium oxalate releases oxalate ion. Then oxalate ion decolorizes permanganate, whereas fluoride ion cannot decolorize permanganate. This is the only test available so far with our inorganic practicals qualitative analysis so far. Okay, but we are trying to develop novel sensing materials which can detect first qualitatively as well as determine quantitatively the fluoride ion. Okay, so the letter F is a significant letter in the periodic table. You will understand the significance after the end of this lecture, but it has its own special feature that this letter we don't want to have in our grade sheet, F. Okay, but it is very significant. It is an interesting ion. It is neither the pollutant nor an essential element. It is either pollutant or as well as a significant essential ion, right? So fluorine, since it occupies the last position in the periodic table, it is being highly electronegative. Always it exists in the form of fluoride ion. There is no fluorine molecule exist in the in our earth. Okay, we have bromine molecule, we have chlorine molecule, we have iodine molecule. They can exist as bromide ion, chloride ion, iodide ion, as well as simple molecule Br2, Cl2 and I2. But as far as fluoride is concerned, it always exists in a combined form, that is fluoride. So there is no fluorine hereafter, only fluoride. Okay, F minus always is, it exists as F minus and combined with different types of cations. Then as far as sources is concerned, fluoride ion present only in the earth crust. We have to go deep into the earth crust, at least 10 meters. So I have listed some common fluoride bearing minerals, namely fluorospar, cryolite, calcium phosphate, apatite. So these are all the three major fluoride bearing minerals which is available only in the earth crust. So in the earth surface, there is the availability of these minerals is very minimum or almost nil. Only deep in the earth crust we have these fluoride bearing minerals. So the fluoride source is the deep well water or bore well water, not the surface water. For your information, rainwater, seawater, river water, pond, surface water, like water present in the ponds, are free from fluoride ion. This is because these minerals are absent in the earth's surface. These are present only in the deep earth crust, at least 10 meters or beyond 10 meters. So only borewell waters and deep well waters will have this fluoride ion. So dissolution of these minerals is the source. It is the natural source for fluoride ion. Of course, there are industrial smokes which can liberate fluoride ion. It is very minimum, but these three minerals contributes the major natural source for fluoride pollution in drinking water. Okay, so hereafter no more fluorine F, it is always F minus fluorides, right? As F is being more electronegative. Then, as I told you earlier, fluoride ion is an essential ion. So, it can prevent dental caries. What is actually dental caries? Our teeth contains a compound known as hydroxyapatite. The hydroxyapatite is also present in our bone, but since it is used as a medicine for reducing tooth decay, I told you that our teeth contains hydroxyapatite. This hydroxyapatite, a calcium containing compound, is relatively more soluble in acids. So, as saliva secretes, the hydroxyapatite can slowly dissolve in that acidic hydrochloric acid of the saliva. So, it results in the decay of tooth, right? That is known as dental caries. So, when the hydroxyapatite is treated with fluoride ion, gets converted into a compound known as fluorapatite. That fluorapatite is relatively less soluble in acids, thus it prevents dental caries. Okay. So, in this sense, fluoride is used as a medicine, and that therapeutic method is popularly known as fluoride therapy. So, some anions are essential for biological function, some anions are toxic even at very low concentration. This anion, this unique anion, fluoride ion, is under this condition it is used as a medicine. So, it is essential. So, that is why all our toothpaste contains fluoride in the form of sodium fluoride. The concentration will be around 0.01%. Though it is minimum, it is essential. Every toothpaste which is available in India contains sodium fluoride or potassium fluoride, fluoride ions in particular, in the concentration range of around 0.01%, right? So, it is to prevent the dental caries, right? See, when the concentration of fluoride ion increases beyond certain level, so here I have given us greater than 1.5 milligram per liter or 1.5 ppm. Say this is the permissible limit set by WHO for fluoride ion, say 1.5. Say once in 5 years, WHO will revise this concentration, but for almost 15 to 20 years, they are still maintaining this concentration. So, the permissible limit of fluoride ion in drinking water, according to WHO, is 1.5 milligram per liter or 1.5 ppm. Right. If the fluoride ion concentration in drinking water increases, more and more fluoride ion accumulates in our body, what happens? It affects almost the entire body, teeth, bones, muscles, even blood corpuscles, WBC. It can affect almost all the parts of the body. So, this ion becomes a pollutant. It becomes a poisonous substance. Even for your information, consumption of 4 gram of sodium fluoride in single dose can cause death also. So, fluoride ion at very low concentration, it is used as a therapeutic medicine, right, to prevent dental caries. But at higher concentration, it becomes a pollutant. So, in that sense, fluoride is a unique anion present in the universe. Okay, so the ill effect or the beneficial effect of fluoride ion depends upon the concentration. So, when the concentration of the fluoride ion exceeds 1.5 milligram, it almost affects all the parts of the body, right? So, the disease caused by the excess intake of fluoride ion is known as fluorosis. It is a common term. There are 3 types of fluorosis. One is dental fluorosis. Initially, it affects the teeth alone. Then skeletal fluorosis. If the concentration increases beyond certain level, it's going to affect the bones also. So, it is known as the first one dental, the second one skeletal fluorosis, and the third one is non-skeletal fluorosis. There are 3 types. Non-skeletal fluorosis affects the WBC as well as the muscles, particularly the muscles in the lower abdomen becomes very hard. So, fluorosis is a crippling, painful disease caused by excess intake of fluoride ion, right? Fluorosis, right? Then how fluoride ion can enter into the body? What are all the sources? Say here I have listed some sources, some dominant sources, out of which the drinking water is the main culprit. It is the main source. I can say it is 95% of the fluoride ion or even 99% of the fluoride ion which is present in our body enters through drinking water, particularly deep well water or borewell water. Okay, drinking water is the main culprit which brings fluoride ion into our system. Of course, as I told you earlier, our toothpaste contains 0.01% of fluoride. There are some of our friends have the habit of eating toothpaste. So toothpaste will bring fluoride ion into our body. Of course, dust fumes, and food materials cultivated using this drinking water will have trace amount of fluoride. Mouth washes and mouth rinses can also bring fluoride ion into the body, but drinking water is the main source by which fluoride ion can enter into our body, right? Say this picture you might have seen commonly in rural areas, even among your friends, even among school going children and college students. Say the first picture, you can see the yellowing of teeth occurs. Say nature has a color test for fluoride. So this is dental fluorosis. Say this yellowing of teeth is caused only because of excess intake of fluoride ion, nothing else. என்ன ரீசன் சொன்னாலும் நம்பாதீங்க. This is the only reason. Fluoride ion causes yellowing of teeth. This is known as dental fluorosis. The first picture is the initial stage of dental fluorosis. Then the second picture is the acute stage of dental fluorosis. Okay, so the yellowing of teeth is a very common sign in many areas of India. Just you can see just yellowing, and it starts from the edge and moves up. Okay, so yellowing of the teeth. So in our inorganic qualitative analysis, we don't have any color test for fluoride, but nature has a color test for fluoride, right? Yellowing of teeth. So I request all my chemistry teacher friends, whenever if you come across any such yellowing among your students, tell them your drinking water contains excess fluoride ion. Then for your information, there is no clinical treatment is available for any form of fluorosis. Even say dental fluorosis is the initial stage, then comes skeletal and then non-skeletal. Okay, so tell them, advise them to go for fluoride free drinking water, or advise them to take more amount of calcium. Only calcium can precipitate fluoride in the form of insoluble calcium fluoride, so that our urinal system can excrete that excess calcium or excess fluoride ion. Okay, so this nature has a color test, but we are struggling to find a molecule which gives a color with fluoride ion, right? So this is dental fluorosis. First one, there is no clinical treatment. If you go to the dentist, what will they do? What will they do is just they will scratch the yellow color and give a polymer coat over the teeth, but it is not the remedy. The remedy is prolonged use of fluoride free water or excess intake of calcium rich millets, particularly the ragi. In Tamil it is known as kelvaragu. You take more amount of millets, so that calcium rich food, so that it can be removed. So here I want to stress a fact that our RO plant which is available in our home, it removes calcium. It will not remove fluoride, or it will not remove any other anion. It will remove calcium and magnesium ion. So it is against fluorosis, right? So if you take the raw water as such, more amount of calcium and magnesium will enter into our body, so that it can remove fluoride ion. But of course, excess calcium will give some other impact, that is different. So in those days, we have a MBBS doctor who is known as a family doctor, who knows the entire history of our family. Now that we have specialists, if you go to a dentist, they will ask them to take more amount of calcium. If you go to an urologist, they will advise you to take less amount of calcium. Otherwise, calcium oxalate will be precipitated as stones in the kidney. Okay. Now the things have changed. We have a specialist for right hand and we have specialist for left hand. So it is not an universal truth, but to avoid fluorosis, take more amount of calcium. That's all, right? Say this is skeletal fluorosis. Say these two photographs were taken from Rajasthan. Rajasthan is the worst fluoride affected area in India. Okay, so I am very particular in taking these two photographs. Look at this. This is because the age is immaterial. A young boy as well as an old lady, they are affected by skeletal fluorosis. What happens is, due to the accumulation of fluoride in the bones becomes very soft. Look at that. The bones become very soft. So age is immaterial. Only the concentration of fluoride which enters into our body is material. Okay. So even it can affect young children or very age-old ladies. Not only human being, it can affect all the animal kingdom, including horse, cows, and goats. It can affect the animals also. So this is acute stage of skeletal fluorosis. So initial dental fluorosis, then comes skeletal fluorosis. So these are all the facts to stress the importance of fluoride ion. Okay. Then of course we have non-skeletal fluorosis. There is no exact picture is available for non-skeletal fluorosis. It affects the muscles. Say bones become soft whereas muscles become hard. Particularly the abdomen muscle becomes very hard as a result of non-skeletal fluorosis, and the WBC is very much affected. But till today, the exact mechanism of action of fluoride in our body is not clearly known. This is because dentists, they are doing their research with their knowledge, without the knowledge of chemistry. Similarly, biochemistry. Biochemists, they have their own way of doing research with fluoride ion. Chemist, we are doing in some other way, how to remove fluoride ion or come to what are all the ill effects of fluoride ion, something like that. We are concentrating more on chemistry. To remove or to study the fluoride mechanism in our body, it should be a collective effect. All should come together and work together to find the exact mechanism of action of fluoride ion in our body. See, there is an International Society on Fluoride Research. It is in New Zealand. They are having a journal, Fluoride. The name of the journal is Fluoride. If you look at the editorial board of that journal, majority of them are doctors, not chemists. So it is very difficult to pinpoint the mechanism of action of fluoride ion in our body, right? So this is an observation. The severity of skeletal fluorosis is generally less in women than in men. So women are fortunate. They are less affected when compared to men. See, this is an observation by UNICEF, right? So why? There are two reasons. One is our sociological reason. Another one is scientific reason. First, let us see the social reason. Say, if you look at Pollachi or Coimbatore, they are relatively fluoride-free areas. Then if you look at Dindikal, where I am sitting now, is a fluoride endemic region. It contains relatively more amount of the concentration of fluoride in drinking water, in borewell water will be greater than 1.5. We have up to 3.6 milligram per liter. Okay. So a girl born in Coimbatore will be exposed to less amount of fluoride during or up to 25 years before her marriage. Then suppose the girl is married to a boy in Dindikal, what will happen? She will be exposed to higher concentration of fluoride only in the second half of her life. So in that sense, she will be free during her first half and she will be exposed during, suppose if he is married to a boy in Dindikal. Similarly, a girl in Dindikal, if you got married to a boy in Coimbatore, during her first half, she will be exposed to more fluoride, and the second half, she will be free from fluoride containing drinking water. So, in that sense, girls are lucky. So, they are transformed from free area to endemic area or endemic area to free area. Don't ask, suppose a girl born in Coimbatore get married in Coimbatore itself. So she is lucky as far as fluoride is concerned. Similarly, a girl in Dindikal, she will be exposed to higher concentration of fluoride throughout her life. At least girls have a chance to move from endemic area to fluoride free area. So this is social reason. Say this is according to UNICEF, right? Then the scientific reason is, suppose if more and more amount of fluoride gets into our body, whether our body has any mechanism to excrete fluoride ion, yes, it can excrete fluoride ion through urinary secretion. But how much it can excrete? It only very little amount of fluoride ion can be excreted. It depends upon the individual. Say this is common to men and women. But in the case of women, in addition to urinal secretion, your menstrual secretion, your menstrual cycle can also excrete fluoride ion from your body. So in that sense, you are lucky enough. So urinal secretion as well as menstrual secretion can remove excess fluoride ion from our body, your body. So that is why women are safe, relatively safe when compared to men as far as skeletal fluorosis is concerned, right? See this picture, look at this picture. This picture is released by UNICEF regarding the availability of fluoride containing drinking water or map of fluorosis. Look at that. The blue colored regions are worst affected, or they have drinking water, borewell water, which contains more than 1.5 milligram per liter of fluoride ion. So throughout India is affected by fluorosis. That means every borewell water has fluoride in Indian region, Indian peninsula. Okay, so entire India is affected. Not only India, China, the entire Australia, of course, some parts of America and so on. But this region, the Ethiopian, Uganda, this region, they are the worst affected region. Say we are talking about the concentration of 1.5 milligram per liter, 1.5 ppm. If you look at the concentration of fluoride in this area, Ethiopia, Uganda, Kenya, Tanzania, in this area, there are borewell waters which contains nearly 1 gram per liter. So 900 to 1000 milligrams per liter fluoride has been reported in this area. So where the dental fluorosis is a very common sight, yellowing of teeth is a very common sight in Ethiopia and Uganda region. Of course, dental fluorosis, not only dental fluorosis, skeletal fluorosis is also very worst in this area. So entire Indian region, entire India has fluoride bearing mineral. So this is only because of the geological sedimentations. Okay, it is only because of the presence of fluoride bearing minerals in this area, right? Nothing else. No man-made activity, only natural source, right? See, this is the picture as far as India is concerned. So look at this. In this Rajasthan region, particularly West Rajasthan region, the highest concentration reported is 47.5 milligrams per liter in the border of Rajasthan and Punjab. Okay, so West Rajasthan is the worst affected region, which contains the highest amount. 47.5 milligram is the highest reported so far. And as far as Tamil Nadu is concerned, here it is marked as the Erode. Actually, the Dharmaburi region, okay, north of Erode, Dharmaburi, Krishnagiri region, they recorded the highest 7 milligrams per liter in Tamil Nadu. So they are all the worst affected area. But, so look at these areas. Say these areas are Dindikal, Ramanathapuram and so on. They have, in Dindikal, the highest concentration reported is 3.6 milligram per liter. Okay. I know all these data only because, as I told you yesterday, here we have one professor Meenakshi, who is doing research, active research in the area of fluoride, okay, mapping of fluoride and removal of fluoride. So I have collected all this information from their laboratory only, right? Right. So our ultimate aim is to detect fluoride ion. We have so far we have only calcium ion. So all these facts emphasize the importance of fluoride ion. So fluoride ion detection determination is very important. Yes, no doubt. It is most significant ion. It is unique ion. So the concentration of the fluoride in drinking water should be monitored. We need to have a sensor or an agent which can detect and determine the fluoride ion. Say this is one of the such report, a sensor. It is known as alizarin test. This is the only test color test available till today for fluoride ion. Say the dihydroxy naphthoquinone anthraquinone is known as alizarin. When zirconium is added to that, these two phenolic OH will be deprotonated and it forms a zirconium complex. That zirconium metal ion abstracts and bind with fluoride to impart color change from purple to yellow. So this is alizarin test. So it was reported in 1932 in Journal of Chemical Education by Irwin Stone. Okay. So long back it was reported. Then followed by that work, many group they have tried to analyze, detect and determine fluoride in drinking water. Okay. So these are all some of the works. Look at this, 1945, 55, 47, 51, they are age-old works. Almost all these works are titrometric works. So whenever they report any estimation of fluoride, in those days they don't have any sophisticated instruments, so only titrometric method. Majority of these methods based on alizarin only. So modified alizarin or with other metal ions and so on. So even right from 1931 still today we are struggling to have to detect a molecule, to establish a molecule which can give a color test with fluoride as well as used to determine fluoride in water samples. So what are all the classes of sensors available for fluoride ion? Say, look at this. We know that fluoride is exists only in the form of F minus. So being highly electronegative, it can form strong hydrogen bond. So urea thiourea, which possesses NH, an acidic hydrogen, can form hydrogen bond with fluoride ion. So they dominate the major work in the area of fluoride sensing. Majority of the work is reported with urea and thiourea. Of course, some amides, right? So amides also have NH, acidic hydrogen. Similarly, indoles and pherols, they have hydrogen and hydroxyls, phenolic hydroxyls. So all these four classes of receptors, they utilize hydrogen bonding ability of fluoride ion. Say, as far as cyanide is concerned, cyanide can make hydrogen bond with these acidic hydrogens, as well as cyanide can undergo nucleophilic addition with CC bond or CN bond or CO bond. But fluoride ion cannot undergo such chemical reaction, such addition reaction with C double bond, C or polar bonds. So we have to utilize majority of the hydrogen bonding sensors. So these are all hydrogen bonding sensors. Then metal centers, like our alizarin test, zirconium attracts fluoride, coordinates with fluoride. Similarly, some metals can coordinate, and charged species. Some positively charged species can attract electrostatically the fluoride ion from solution so that it changes its optical property. So these are all the different classes of fluoride ion sensors reported so far. So these are some examples. Say Lewis acid base concept. Look at that. We have boron, mercury, and zinc can act as Lewis acid, so it can attract fluoride ion. So it can bound with fluoride ion, thus a color change or fluorescent change or electrochemical change which can be visualized. So Lewis acids can be used, particularly boron, many boron containing compounds. So this is just to show that it is an example where Lewis acid-base chemistry is used to detect fluoride ion. Similarly, this one, look at this boron on treatment with fluoride, the boron oxygen bond gets cleaved and boron fluoride bond is formed. This compound is magenta in color and it undergoes decolorization. So this is some of the examples of Lewis acid base chemistry. A colorimetric test, a color change from magenta color to pink color to colorless, right? So this is a reaction based fluoride sensor. Just the decellylation occurs. The OSI bond gets glued due to the action of fluoride ion. A colorless solution becomes pale yellow in color. Okay, this is another strategy by which fluoride ion can be determined or sensed, recognized. Okay, let's look at these examples. Say in the first case we have urea or thiourea. The second case again the amide CONH bond. Since we have ferrocene, the change in electronic property can be determined or investigated using electrochemically. So this can be used as an electrochemical sensor. Look at this complex, a ruthenium complex. At the corner you have an NH. So this NH can make hydrogen bond so that the optical property of the complex where we can identify either color change or fluorescent change. Similarly, this NH. So these are all some of the examples reported. So if you look at this, majority of the complexes are utilizing the hydrogen bonding ability of the sensor molecule. So here you have a positively charged phosphorus. So this phosphorus can attract fluoride ion electrostatically. So this is an ionic species, right? Then if you look at the pKa value of hydrogen fluoride, it is relatively highly acidic so that it can undergo ionization more easily in aqueous solution. It furnishes fluoride ion so easily. Okay, hydrogen fluoride is a strong acid as far as the pKa value is concerned. Okay, so what we have done, what we have visualized, how to find out how to detect fluoride ion in water. So this is the first compound we have reported during 2013. We have published this work in Dyes and Pigments. So since I told you earlier, we are working with the quinone moieties. Then we have constructed a urea here, thiourea here. Also, of course, we have constructed both urea and thiourea. What is the advantage of this quinone? So when quinone is directly attached to the urea NH, there is a intermolecular charge transfer. Since quinone is electron accepting, electron withdrawing group, it withdraws electrons from the nitrogen. So this hydrogen is relatively more acidic than this hydrogen, though it is present nearer to the carbonyl group, which is also electron withdrawing. Look at this NMR, proton NMR signal. This proton appears at 11.7, whereas it appears at 12. So this is relatively more acidic. So here this NH is relatively far away from the quinone. So what we have done is we have constructed another molecule where the NH is directly attached. Look at this NMR signal. Now this acidity, the signal for this proton is 13.3. So it becomes more acidic. Since the electron is removed through intramolecular charge transfer from nitrogen, the lone pair is removed, it becomes more delta plus or more acidic. So we thought that this can make hydrogen bond more easily with the fluoride ion in aqueous solution. So if you look at this impart a color change. Both the receptors, first one, second one, anthraquinone based and naphthaquinone based, they impart color change from yellow to intense red due to hydrogen bonding. But unfortunately, this works only in acetonitrile. Even if a small amount of water, a single drop of water is added to this solution, immediately it undergoes decolorization. This is because fluoride ion loves water. The hydration energy is in the order of 500 kilojoules per mole. So When even small amount of a drop of water is added to this red color solution, immediately it undergoes decolorization, though it forms a strong complex with these two receptors. So these protons are more acidic, so that it can bound to these protons strongly through hydrogen bond. And of course, this is possible only in astronitrile, only in organic media, not in aqueous media. So we have characterized this one. So deprotonation occurs. These two protons are responsible for these two, one at 12 and another one at 13.3 ppm. So these two protons undergoes deprotonation. After addition of one equivalent, both the protons disappear. So this is the mechanism. So the sensor works through hydrogen bonding and deprotonation. So this is the mechanism. Just one fluoride ion can interact with both these hydrogen ion simultaneously. So this is confirmed through Jobs method, or by determining the stoichiometry. So one molecule of the sensor reacts with the two molecule of fluoride. The stoichiometry is 1:2. So both these molecules simultaneously attracts these two hydrogen atoms and deprotonate these two hydrogen atoms. And of course, we have used some theoretical calculations also. Say, look at this binding constant value. Say, for this compound, the binding constant value is in the order of 10 power 8. But for this compound, which possesses a strong acidic hydrogen atom, 13.3, the binding constant is in the order of 10 power 15. So it is extremely strong binding. Even if the binding constant is in the order of 5 and 6, it is termed as strong binding. Look at that. This particular sensor was found to have a binding constant in the order of 10 power 15 per mole. So the fluoride binding with these two NH is extremely strong. But unfortunately, it works only in organic solvent, astronitrile, but not in aqueous solvent. But we are able to detect the presence of fluoride in toothpaste. So the S1, S2 are sample 1, sample 2. After adding fluoride ion, so after adding the sensor, the same red color change we are able to see in toothpaste. We dissolve this receptor in astronitrile. We prepared a suspension of toothpaste in water. Then we have added that, it works, right? Then, see, this is a designing of another one. So we want to have more acidic NH proton, NH. What we will do that? Say, look at this compound, which is commercially available, or we can prepare from dichloro or dibromo derivative. Say, here also we have charge transfer from these two nitrogen atoms, but since we have two nitrogen atoms, the charge transfer, there is a competition between these two nitrogen atoms. So the proton acidity is very small. It is very weakly acidic. The signal is 5.462 only. Now, an electron withdrawing imine is constructed with the 1NH2. So we know that CIF base, imines are electron withdrawing. So this also withdraws electron. Now this nitrogen alone can form intramolecular charge transfer. So the acidity of the proton increases 5.4 to 6.9. Then the benzimidazole. The benzimidazole as such has a strongly acidic proton, namely it possesses 12.5 ppm the proton NMR signal. So we thought that why not construct such type of imidazole here. So we have prepared these type of imidazoles. So this is the basic chemistry behind that. Try to have a more acidic nitrogen NH group in the molecule. So thiophene will act as an electron withdrawing substituent. Quinone will act as an electron withdrawing substituent. So the NH acidity becomes 14.94. So we have prepared a series of similar imidazoles. So we have prepared all these imidazoles. Look at the proton signal values. We are able to vary the proton signal values from 13.7 to 14.94, where the thiazole is the substituent. So we thought that only acidic hydrogen can make hydrogen bond with the fluoride ion, so that it impart. So once the fluoride ion binds to this NH, the charge transfer from this nitrogen to quinone will vary, naturally color will vary. So here quinone moiety will act as a signaling unit and the NH moiety will act as a receptor unit. Interestingly, the sensor gives a color change with fluoride as well as cyanide, but unfortunately only in DMSO. Okay, so if you look at the binding constant of these receptors, these 8 receptors, and the proton NMR signal of these receptors, they are almost linearly correlated. Okay, one for the black color line for fluoride and the red color line for cyanide ion. So more the acidic of the proton, more will be the binding constant, right? So our perception is right, but we are not able to accommodate water here. So only if you add just a single drop of water, the red color will be decolorized, right? Of course, we have prepared some test strips using filter paper, right? So the same imidazole, quinone imidazole, we have introduced an ferrozine just to whenever there is a change in after binding fluoride, change in intramolecular charge transfer, naturally there will be a change in the electronic amount of electron density on the ferrozine. We can record it electrochemically. So we have tried that. Since the color change colorimetry works only in organic substance, we are trying to prepare an electrochemical sensor. Here we are able to accommodate some amount of water, and we have reported these 2 sensors, one in naphthaquinone and another one is anthraquinone. Okay. These 2 receptors here again shows the same color change, but in DMSO only, in organic solvent only. But electrochemically, we are able to see some change in aqueous solutions. Similarly, here what we have done is we have fixed the NH and we have varied the acceptor unit. Instead of quinone, we have varied some other acceptor units. So here again, the color change. One of the acceptors shows a color change with the fluoride ion from pink to green. Similarly, pale red to intense blue with the fluoride and cyanide, one of the acceptor. But both these acceptors do this colorimetric change only in DMSO due to deprotonation. NMR titration indicates that deprotonation is the main mechanism behind this. Okay, so here again we are not able to accommodate water. What we thought that, so we have gone through this literature. Some complexes are being reported in literature. So in the 50% aqueous THF, this coordinator water is replaced by fluoride ion. So colorimetrically or fluorimetrically they are able to see some change. See here, this compound can accommodate 20%. This OH can bond make hydrogen bond. So there is a conjugation up to the metal center. So optical property varies. Similarly, this NH can make hydrogen bond in aqueous solution, right? So if you form a complex, the whole molecule, whole organic ligand, whole organic receptor can be brought into an aqueous solution. It can accommodate water. So this is our perception. Similarly, these complexes. Okay. So it uses this NH. Similarly, this NH. The NH which is far away from the metal center is used to sense fluoride ion. But here if you look at this NH can make hydrogen bond with fluoride and cyanide. This NH can make hydrogen bond with fluoride, acetate and dihydrogen phosphate ion. They are not so selective towards fluoride, but they can be used. So complex can accommodate water. This is our idea. So already we are working with quinone, where the NH is directly attached to the quinone, which is capable of forming hydrogen bond with the fluoride ion or any anion for that matter. Then the quinone will act as a signaling unit. Suppose this nitrogen is made to coordinate with the metal center in the form of a complex. Since we are removing electron density from the nitrogen through coordination, this hydrogen will become more acidic. Already it is in intramolecular charge transfer with quinone. Now the remaining residual electron is drained through coordination, so it will become more acidic, number one. Then this entire complex may be soluble in water or may accommodate some amount of water in the medium. So this is our basic idea. So same quinone NH, we brought a complex. So this is the first complex what we have reported with cobalt and nickel. So we have selected the ligand in such a way that we have NH as well as another coordinating atom in the form of pyridine. So we have formed a complex, but this complex also works in astronitrile. It doesn't accommodate water, maybe due to the presence of large organic quinone moiety. So there is a color change from yellow to blue, intense blue. The color change is good, but it works only in astronitrile. Look at this. In astronitrile, cobalt complex shows an intense blue color, a very dark blue from a colorless solution. Similarly, nickel also. Excuse me. So if you look at the binding constant, they are in the order of 10 power 8. So they are highly selective towards fluoride. These are all okay, but it doesn't accommodate water. So this is an interesting work. So we know that ethylene diamine is a strong ligand, a well-known coordinating ligand, a bidentate ligand. So we have constructed a similar molecule, NH directly attached to quinone. Suppose if you have ethylene diamine, this NH2 can also interact with chloride, so it will cyclize. So to avoid that, we have taken NN dimethyl. So NN dimethyl ethylene diamine. It is very simple reaction in ethanol. Just stir it, the NH will react with NH2 will react with the chlorine to form this molecule. Then with metal chloride, salt, copper, nickel, cobalt, and zinc, we are able to prepare some complexes. Here we have prepared the resulting complexes are 4 coordinated complexes. So ligand. This ligand is soluble only in water, so it shows a color change from yellow to intense blue in DMF, right? Then, fortunately, among these 4 complexes, zinc complex can accommodate 50% of water. So 50% 1:1 aqueous DMF shows similar change in blue color from yellow to blue. Okay, so our perception is right. The NH becomes more acidic and the complex can accommodate water. So this is our first breakthrough wherein a coordination complex can be used. But there are literatures, as I told you earlier. This is the work done in our laboratory. So similarly, look at this. Imidazole, you have NH, then pyridine. There are 2 nitrogen atoms similar to this ethylene diamine. So we have we have prepared this ligand. There is a color change from yellow to brown, reddish brown. So zinc complex shows similar color change with the cyanide, and the nickel complex shows a color change with fluoride. But we are not able to pinpoint the exact mechanism why this. Of course, now it is theoretically possible, and those days we are not able to say why it is selected towards nickel complex is selected towards fluoride and the zinc complex is selected towards cyanide. So in both the cases, it is hydrogen bonding followed by deprotonation. It is the mechanism. Okay. So here we are able to accommodate 50% water. It is 1:1 aqueous DMF. So our perception is right. So in this line, we have prepared many complexes. So first in the first work with the imidazoles, we have reported 8 imidazoles. So these 2 are among the 8 what we have reported. Then we have introduced a hydroxyl group here. Say there is an observation that if you have more and more binding sites for an anion, the selectivity will increase. Say these 2 receptors shows a color change from yellow to red only, in organic medium in DMSO with both fluoride ion and cyanide ion. But with the introduction of a simple hydroxyl group in this molecule, the same color change in aqueous DMSO, which contains 70% of water, exclusively with the fluoride ion. So introduction of additional binding site will increase the selectivity. Of course, introduction of this polar OH group also accommodates water. So these 2 receptors exhibit similar color change with fluoride ion selectively. So this is one. Then you have nitrogen atom, you have phenolic OH. We can prepare complex. This nitrogen and this bond can be rotated. So this phenolic O minus and this nitrogen can form coordination complex, right? So this is the complex. Look at that, an imidazole, phenolic OH. This can coordinate with the metal center. Say, to our delight, we have prepared cobalt, nickel, copper, and zinc complexes. Well-known metal ions. These metal ions are selected because they are known to form variety of complexes. So this system accommodates 80% of water, to our delight, right? So it shows a color change from yellow to red with selectively fluoride ion. The binding constant is in the order of 10 power 7. Since there are two NH group in the imidazole, the stoichiometry is 1:2. First fluoride is attached to this hydrogen and the second fluoride here. Okay, so it accommodates 80%. So our perception is correct. Prepare a metal complex so that we can improve the hydrogen bonding ability of the NH group as well as we can accommodate more amount of water. This is our perception, and the perception was found to be correct. Say, similarly, nitrogen and thiophene. So 70% water, the nickel complex is selective towards fluoride ion. This is another work. Color change from yellow to intense blue. Okay, so as I told you earlier, the sensing of fluoride. Fluoride is a significant ion, has its own unique property. The sensing is in aqueous solution is difficult due to excess very high hydration energy in the order of 500 kilojoules per mole. Okay, so we find to have a molecule which can impart visible color or fluorescent change in aqueous medium for fluoride ions. Okay, thank you.
Thank you, sir.
Okay, once again, I wish to thank my professor, Professor Karthikeyan, and of course, these four research scholars, Satish, Manivannan, Parthiban, and Jayasudha. And for three of them are now in Korea as postdoctoral fellows. So, particularly Manivannan and Satish, they have done excellent work in the area of organic synthesis. See, just I have given idea, they have synthesized all these molecules. So, since they have experience, synthetic experience in company, they have worked in Syngene Biocon for about 4 to 5 years. They are good at organic synthesis. They are able to prepare many receptors, what I have shown today. So, and all my research group, of course, this complex system was funded by CSIR in the form of a project. So, how metal complex can improve the selectivity and sensitivity towards fluorine in the aqueous solution. Thank you, friends. If you have any query.
Thank you, sir. Thank you, sir. Dear participants, kindly share your questions. Participants, kindly share your questions.
काय ना
Professor, good afternoon, Professor.
Yes, good afternoon.
I'm P.A. Perisami from Dr. Magal Engineering College, Pollachi, Professor.
Sir, please.
Whether we can use the fluorimeter for the determination of this?
Yes, we have ion selective electrodes. Lanthanum based ion selective electrodes available in the market. It is relatively costly. Not only that, the electrode lifetime is just only 1 year. So every year you have to change the electrode. Like our pH meter, ion selective electrodes are available in the market, no doubt. But we want to have a reagent which can use a visible color change, a colorimetric reagent which can be used in the laboratory or in the field. We cannot carry the ion cell electrode in the field for water testing, environmental testing. So the scientists are struggling to prepare a receptor. Okay, we have ion selective electrode in the market. For but all the fluoride estimations are being done with that electrode only.
Okay, sir. Thank you.
Okay, thank you.
Sir, one more question. What's your view
Yes.
on halogen bonding? It's asking for Swaminathan.
Halogen bonding.
What's your view on halogen bonding?
No, I don't have any idea regarding that. Since we are working with and selective electrodes with fluoride ion, I have less or no idea regarding halogen bonding. We are concentrating more on hydrogen bonding. Sorry, I'm sorry.
Thank you, sir. Participants, any more questions?
So organizers, I am very sorry. Since I have a meeting immediately after this, I have to finish it off around 1 o'clock. Okay.
Thank you, sir,
So,
for your delightful demonstration of fluoride anion sensing from alizarin test to current anion receptor. Really, we enjoyed and thought to have visit to your research. Thank you very much, sir.
okay, thank you, friends. Once again, I thank the authorities of NGM College Pollachi, particularly Pungudi Madam, for giving me this opportunity. Thank you, friends, and I am sorry since I have some other important work in the university. I am finishing at before my schedule. Okay, thank you.
Dear participants, kindly switch on your video for photo section.
Madam, I think video is okay. Now it is okay, madam.
Yes, sir. Thank you, participants. Now it's time for a lunch. Participants kindly rejoin in the next section at 2:30 p.m. Thank you.